ramp loading, right? Ramp type of loading with a rise time of, we are truncating it at TR, the amplitude of P naught. So this is PT versus time T, and another load that we have considered. So this is a step load. So they suddenly applied and it remain the same. Okay, so that is P naught time. And we have seen that the responses due to this ramp loading is obtained as this. Okay, so this can be obtained using both approaches, that is the classical approaches as well as the Duhamel-integral approach you can obtain. Okay, and we have done in the last class, right? So this is P naught by K, T by TR, this thing that we have obtained already, and this is also we have obtained for this step load. Okay, step function load basically, and this is the ramp function load. So this is the ramp function load, and this is the step function load. So and for this we have obtained this for the undamped system, right? So the damped system there is some little bit more involved the expression, but this is simplified for the undamped system. Okay. Now what we are going to consider is the step force with finite rise time. Okay, because this step force, you see, whatever you suddenly applied or what fast you applied, it is, I mean, it is impossible practically to apply a load, I mean, in zero time, right? Just P naught. Okay, so some time is required to reach that P naught. Okay, so that may be large, that may be small, that I do not know. So I mean, that means this can be like this, and then after this, or this can be like this and after this. Okay, so that's why the name is that step force with finite rise time. So anybody has any doubt about these two expressions that we have done in the last class? So this expression, the left hand side expression, is due to the ramp function load, response due to the ramp function load, and this is the response due to the step function load. Okay, so this we have already derived in the last class. It is clear to everyone, right? Okay. If you have any doubt, then you can ask. Okay. So anyway, so now we are going to start the step force with finite rise time. Okay, so let's say TR is my rise time. Okay, so there is some time is required to reach to the P naught, and after that it's remain the constant. Okay, so this is called step force with finite rise time. Okay, okay. So the model that we are going to consider is this thing. So that is a undamped system, single degree of freedom undamped system of mass m, stiffness k, subjected to load PT, where PT is defined through this. Okay. So how can I write the PT mathematically? Okay, so PT I can write, so from 0 to TR. So during this time region, it can be written as P naught T by TR. Correct? Okay. So at T equal to 0, you see it is 0. At T equal to TR, it is P naught. Okay. So T less than equal to TR, it is defined as this, and after that it is just P naught. Clear? Okay. Okay. Now we have obtained how to find out the responses in this region, right? I mean, from T0 to TR. So for the range of time, I can say 0 less than TR, T less than equal to TR. So for this range, we know already how to find out the response. Okay, and that is nothing but this expression that I have written at the bottom of the slides. Okay, so xt is equal to P naught by K, T by TR minus sin omega into omega in TR. Okay. System is at rest condition. We're starting at the at rest condition, and then this is my response due to this ramp load. Okay, which is till TR time. Okay. So now tell me, so how to, now I want to find out the response at any time here. Okay, that after TR, any time. Okay, I want to find at any arbitrary time T. Okay, T which is greater than TR. So for T greater than TR, how I can find out? I mean, how I will get the response. I know the response due to step force, right? But this is not only step force, but here there is some rise. I mean, that's ramp force, some rise time with TR, and then there is a step force. So what will be my response? Just tell me, what will be the response? Not mathematical expression I am asking. I am just saying how can I obtain the responses at the during the constant phase basically. Okay. So during the ramp phase is very easy, right? So that is the same as this thing. Have you already done? Okay. The same as this equation. Okay. So that is same. But after that, there is the constant phase force, and how to find out the response here. Okay. Let's say. So what is will be the xt? So I would say xt during constant phase. Okay. So that is the response during constant phase. In this case. So how I will obtain? Tell me. Not the mathematics. Tell
We
me.
can put PT in Duhamel's integral and then we can get it.
What again? Can you please repeat?
So this PT we have got na P naught T by TR and P naught at particular time interval. So we can put P naught in Duhamel's integral and get the value.
No, the I don't understand, because how will you get it here? Because it has some effect on this, right? It has already some effect of the ramp force. So how are you going to consider? Yeah, superposition. Okay, so superposition is there. So what we can do is that, so due to we want to use the expression that you have already obtained, right? Okay, so we know that the response due to this ramp force is this, and response due to the step force is due to this for the undamped system. Okay, so how to use this expression? Okay, I want to use this because this we have already done for the step force, but here before the step force also some ramp force is there. Okay, so this ramp force at the end of time t equal to tr. Okay, see, so at t equal to tr, the ramp force is finished, right? But it has some displacement velocity, so it is imparting some displacement velocity to the system. Okay, so basically, so I can write the response during this constant phase can be written as that the phi vibration part, or should I say phi vibration response, correct? Phi vibration response due to the initial displacement velocity imparted by this ramp force. Okay, so that actually basically I should say phi vibration due to xtr, right? Because x at tr and x dot tr, because that effect is there. So that part at the end of ramp phase, right? At the end of ramp loading, then plus this one due to effect of this. Yeah? So due to, and then the response due to step load, but it is starting at t equal to tr. Okay, starting at t equal to tr. So that is the thing I want to say. Okay. Clear? So if this is the case, how can I write my total response? This is what, this is not required. What is this? So again I am writing here, so xt. So xt can I write like this? So I will write, so due to initial condition, that means x tr and x dot tr. What will be my response? Tell me, undamped vibration, undamped vibration. What will be the response due to this initial displacement and velocity expression?
So xtr cos omega n
So omega n
tr
t minus tr,
t
right?
minus tr plus x dot tr divided by omega n
Omega n
into
sine
sine omega n t
omega
minus tr.
plus t. So that is due to the initial condition. Then plus due to the ramp load starting at t equal to tr. Sorry, ramp load. So it is a step load starting at t equal to tr. So what is that? Tell me.
I said delta static
Yeah, that is p naught by k. Correct.
into 1 minus cos omega n
Omega n.
t minus tr.
So this part is the p vibration part arising due to this initial displacement and this initial velocity at the end of the ramp phase. Okay, that is the t equal to tr, and this part is the due to the step load, okay, which is starting at t equal to tr for the undamped system, obviously. Okay, both are undamped system. Now I can obtain this, right? Xtr and x dot tr. We know the expression. What is the expression for ramp load? This load, right? This is the for the ramp. So xt I know at any time, so I can find out x at tr, and I can then differentiate it and substitute t equal to tr to get the x dot tr. So just substitute it, and you can simplify further. So are you getting my point? How to get xtr and x dot? This is the, what is this expression? So this is load. We did in the last class also. Let me go here. Okay. You see, using Duhamel integral, we obtain this, right? So xt is equal to this. So here I will put t equal to tr so that I can get x at time tr. I will differentiate it first, get x dot t, then I will put t equal to tr, then I will get this. So xtr and x dot tr. That means basically the displacement and velocity at the end of the ramp phase. That is at time t equal to tr. Clear? Substitute here in this expression xtr and x dot tr, then just simplify it, trigonometric simplification, and then we can get this expression. What is the expression? Let's see. Okay, so I have written here, I can be obtain this thing, so that you done, so you can obtain this expression, that is equation number 15, and obviously this is valid for t greater than equal to tr. Okay, So will you be able to get this expression? Just you can try it. Okay, you try it. So substitute xtr and x dot tr in that expression that I have written and try to obtain this equation. Okay. So you see it is written here xtr cosine omega n t minus tr. So this is for your reference. It is written here. So you just substitute this and this value. Okay, by substituting tr in the expression of xt for the ramp load and differentiate it and then substitute t equal to tr to get the extra tr. Okay, and substitute here, simplify it, and you'll get xt. So just quickly do that. So anybody has any difficulty what I am asking or what I am explaining? Any difficulty in understanding? Very simple, right? So that is that the end of the ramp force, what is the displacement velocity? So that is ensuring a free vibration part. So that is written as this, the left two terms, and then in addition to that, P naught by Q 1 minus cosine omega and T minus TR. So that is due to the step load which is starting at time T equal to TR. So please quickly do this. This is very straightforward. Just trigonometric simplification. That's all. So this simplification you have to do it yourself because this should obviously be not elaborately written in the books, right? So book also you can say that by substituting xtr and x dot tr, we can simplify it by and getting this equation number 15. Okay, that you can do it by yourself. Okay. So please tell me any difficulty in doing this. Are you facing, or you are not able to understand what to put or what to do? Then anybody got the expression?
Yes, sir. Same.
Fine. This is very simple actually. Anyway, so now tell me, so this is the expression, right? Okay, xt or xt, whatever. So tell me, so at what frequency system is oscillating? If at all it is oscillating, then at what frequency it is oscillating?
Omega n.
That is system natural frequency, right? So, okay. So it will oscillate at system natural frequency, okay? During the ramp phase as well as the step phase. So now we are going to plot this xt divided by p naught by k, that is xt divided by delta st. So that we are called as a dynamic load factor, right? So xt by delta st. So this basically this expression we are going to plot for different values of t r by tn. Okay, so we plot this versus t by tn. Actually, this is normal non-dimensional time actually we are plotting. So t actually we are plotting time versus these responses for different values of tr by tn. Why tr is important? Because the rise time, how the response is getting affected by the rise time. Okay, so let's say, so it can be like this, it can be like this, right? Very quickly rising, it can be very slowly rising, right? So how this rise time tr is getting affected? Because after this it is, I mean, the constant, right? So how the rise time with respect to the natural period of the system, Tn is the natural period, right? 2 pi by omega n, Tn equals to 2 pi by omega n, right? So how the natural period of the system, I mean the ratio of the rise time with the Tn is affecting the response, that we are going to see graphically. Okay, let us see. So that is we are plotting, forget about this thing. Okay, so xt by delta st we are plotting versus what you see, the x-axis is t by tn, so what time we are plotting, and for different values of the rise time. Okay, so you see starting from tr by tn 0.5, tr by tn 0.2, 0.2, 0.5, then 1, 1.5, 2, 2.5, increasing slowly. Okay, to 0.2, 0.5, and then going to 2.5. Okay, so tr you see, and also in the figure you can see, right? So here you see how the rise time is more, right? You see 2.5 here, right? You are coming here, and here you see very fast 0.5, right? And you see it here, so it is here 0.5, sorry, 0.2 around. Okay, 0.2, here it is 0.5 around. Okay, so how the response is getting modified, so that plot is done here. So plot of x by delta st versus t by tn for the different values of tr by tn. Okay, and so all the oscillation wherever it is occurring, so it is at the system natural frequency. Okay, perfect. Okay, now, so there are some interesting features which this need to be discussed. Okay, so now you see first starting from the lowest one, so t by t, sorry, tr by tn 0.2, that means what is very fast rising, right? Fast rising, ramp time is very less. Okay, fast rising and then become constant. So you see the response are almost same as this of, it is like just like a step force, right? What is the response due to step force, right? So we have already done that due to the step force. So it is nothing but it is oscillating about this new static equilibrium position, right? That is 1. You remember? So I'll just go back to that figure. Okay. So it is almost like that, and there is no oscillation during this this period. There is non-oscillativity. Okay. So that is quite obvious. So let me go back that figure. Back to that figure. Yes, and you see it. So that is due to the, you see the heading response due to the step function, right? So without damping it will be just continue oscillating, right? So damping there is decay. So there we are considering without damping. Okay, so it is just oscillating about that. Okay, so that thing is happening when rise time is very small. Clear? So like the case for these and these. Is it clear? Okay, so as you can say mathematically that as tr by tn, sorry, tr by tn tends to 0, so the response is similar to that of like a certain force. So that is obvious. So these two cases are discussed separately. Okay, so as the tn by tr is larger, like say 2.5 or more. Okay, so so in that case what happened, can you see what is happening there? So that means the force is increasing slowly, right, related to the tn. I mean the to rise to the p naught it taking time. Okay, so you see in that case this dynamic displacement, right? So this is the dynamic displacement, right? This one, so this dash line is the static, right? So the dynamic displacement oscillate very closely to the static displacement. Okay, so here you see the oscillation, and here you see the oscillation, and let's compare the oscillation here or here or here. Okay, so it is oscillates close to the static solution. Okay, so when it is a slowly applying, correct, it will be better visualized as a mini plot, one more plot, one some separate plot we will do that coming next. So then it will be further more visualization will come into the picture. So just try to see is that, so when the rise time is very small, okay, then it is just behaving like a step force. Okay, the response is due to the step force. Okay, so and that is intuitively obvious, right? And whenever it is larger, okay, that is tr by tn is 2.5 or 1.5 in that range, so you can see it is oscillating, and the oscillation with a small amplitude, right, oscillates close to the static solution. Now what is happening in these cases when tr by tn equal to 2, tr by tn equal to 1, and or tr by tn equal to 3, 4, like that? Okay, what is happening? What is your observation when TR equal by Tn equal to 1, TR by Tn equal to 2 or TR by Tn equal to 3? So what is the observation from the figure? Quick, tell me, what is the observation?
So after a certain time, it's like becoming same as starting displacement.
What certain time? What is the certain time?
The PR, sir.
Yes, then tell after TR it's no system doesn't oscillate, right? This is the static solution. Okay. Any other observation? Carefully by saying it, you are right. So after TR, okay. So when the ramp force is finished, after that is not oscillating. Okay. Then this point. So just carefully see this part. Carefully see this part. Any other observation regarding system displacement and velocity? So I'll give you the hints.
So that is going to maximum and then
Now what is the velocity there at time t equal to TR?
0.
Yes, t equal to TR velocity is 0. So that means if x dot at time t equal to TR equal to 0, then during the, if this happens, okay, and this happens when TR by Tn equal to 1 or TR by Tn equal to T or TR by Tn equal to 3, then the system doesn't oscillate during the this, what is this called, step force, the step region. Okay, so that can be proved mathematically. You can prove it, or that may leave up to you to verify that. Although the derivation is not given in the book, but it is quite simple. You can check it. Okay, so you first find at whether at this condition the velocity is 0 or not, and if this velocity equals to 0, then you can substitute this in the that expression, and you see that what is your response. Okay, so that can be mathematically seen, and the graphically also here you can visualize it. Okay. So let us say that first assume that at TR by Tn or TR by Tn equal to 2, 1, 2 or 3 even. Okay. So this velocity is, let's say, 0. Okay. X dot TR equal to 0. So now just put it back. X dot TR equal to 0. This expression, right? So you can put X dot TR equal to 0 here. Okay. So basically this term got vanished. So just simplify it. Substitute XTR and tell me what XT you are getting. If X dot TR equal to 0. Understood what I am telling you to do? Any doubt here? Anybody? Please speak out if you have. We are saying that at TR by Tn equal to 1 or TR by Tn equals to 2, X dot TR equal to 0. That you can prove again. That you can prove. That is very simple. Okay, that you can just see. So that I am going to come next. Okay. So let us say X dot TR equal to 0. Then is it true? What is XT coming? Just see. Or the graph is just falsely showing something. Very interesting. So find out what is XT. Any doubt here? So at the end of the ramp phase, the velocity is 0. So that's why we are setting x dot TR. TR is the time, right? Rise time equals to 0. So what is the response during the constant phase? We are trying to find it, because this expression xt that is written here is nothing but the response during the constant phase, right? So by setting this x equal to 0, what we are getting? Yeah, done. Anybody done it? Again, mathematical manipulation. Remember that TR by TN equals to capital TN. Okay, TR by TN equals to either 1, 2, whatever you can put it. Okay, 1, 2. Let's say 1, right? 1 is for simplicity. So TR by TN equal to 1. And TN equal to nothing but 2 pi by omega n. That is already known to. Anybody facing any difficulty in doing the calculation? Any difficulty?
Sir, if I'm putting PR between equal to 1 and getting like P not to K, sir, not response.
P not by K, yes. So system doesn't oscillate, right? So it is static solution. Okay. So that proved. So the graph is not wrong. Now we have to show that at TR by Tn equal to 1 or TR by Tn equal to 2, x dot TR equal to 0. So you just differentiate x dot, you just set x dot TR to 0 and see for what value of TR by Tn it equals to leads to 1. You know x dot TR, right? Because you definitely know it because you substitute in this expression. Someone has done that. So x dot TR you know, right? Here you substitute and then you got this expression. So you just substitute, you just set that x dot TR to 0. Set it to 0. Okay, x dot TR, and find out what is the corresponding ratio for TR by Tn. Got my point? So if this is xt, actually I can find very easily x dot t is equal to p naught by k. So it will be 1 by TR, right? It vanished. So then omega n also vanished. So 1 by TR cosine omega n. So this is x dot t. So x dot tr I can find out, right? So x dot tr will be what? X dot tr will be what is that? I forget again. P naught by k. P naught by k 1 by tr. So 1 by tr minus sine, I think omega n tr by tr. If I am correct, I can go back. So cos omega. Okay, so then you just set it to 0. Okay, so if I set this to 0, then what will happen? This is 0, this is 1. So cosine omega and tr equal to 1, right? Find out omega and tr. Right. So omega and tr will be what? 2 n pi equals to 0, 1, 2, 0. Forget about that, is the time 0 actually. No rights, so that we are not interested. So then it is 2 pi by tn, tr, 2 n pi. Okay. So 2 pi cancel out. So tr by tn is equals to n. So 1, 2, 3. Done? Okay. Now what we are going to do? So now another thing is that is we can plot that xt max by delta st. Okay. So DLF, there is a dynamic load factor xt max by delta st. So this can be written as this. So this we can this is I will leave up to you. No? So that is from this expression actually xt. So you can find out the xt max. Okay. And then divided by delta st will obtain this 1 plus sine of pi tr by tn into pi tr by tn. Okay. So it depends only on tr by tn. Okay, rise time with respect to the natural time period. Okay. So now we are showing a plot of DLF versus TR by TN, which is called the response spectrum. Okay. For the step force, remember this is for the step force with finite rise time. So this is the response spectrum for step force with finite rise time. Although this terminology is ideally suited or most commonly used for the earthquake analysis, earthquake response analysis. So there we used to plot the actually the response spectrum is in a standard way. It is defined as the maximum any response, that is maximum response. Okay, in the y-axis, and in the x-axis it is the natural time period. Okay, so that is plot. That's this type of plot is called the, for different values of natural frequency we want to plot the maximum response. So this maximum response can be displacement, can be velocity, can be acceleration. Okay. So depending on that, it's called the acceleration response spectrum, velocity response spectrum, displacement response spectrum, which are most commonly used for the earthquake analysis. Okay, so if you later on study related to earthquake engineering, then you will find out the quite this terminology or this thing will commonly be used. Okay. But this is for finite for the step force with finite rise time. So this is a kind of a response spectrum. Okay, and for shock type of loading that we'll discuss next. So this is called the shock spectrum. Okay, so this is the dynamic load factor. So that is this ratio. This ratio we are plotting as a function of dr by t. Okay, so just whatever you have discussed through the plot or through calculation, you can see from this plot. You see when tr by tn equal to 1, tr by tn equal to 2, tr by tn equal to 3, what is happening? What is the DLF? 1, right? So that means you see just 1. So this part is not coming into the picture at all. So that is system doesn't oscillate. Okay, it is just the static solution it is showing. Okay, so this plot is actually got vanished because this 1 it is showing now. Okay, correct? That also already proved in the previous plot and also proved using mathematical also you have seen, right? Okay. Now you see, as the tr by tn is more than 3 or 4, you can say, the further going, it is saying that the oscillation, system oscillation is very close to the static solution, right? You see here, what is the oscillation, amount of oscillation, and here see here the oscillation. As you go further, the system will further like this. Okay, so that is also proved here, right? You see, as the tr by tn is more 1.5, 2.5, so the system oscillates close to the static solution as opposed to this. So that is also clear from this. Okay, and as tr by tn is very less, let's say near here in this range. Okay, so it's like a step force, right? So when then at that time, what is the DLF? I mean, at the situation, what is the DLF? What is DLF? What is the value of DLF?
So more than one.
Huh?
More than one.
Now tell me what value, I mean, approximately tell me, na? In this region.
1.8 or 1.8.
Huh? What is the value of DLF?
So at 0 it is 2.
Yeah, so it is, as I am saying, in this range, small range, as it is, I mean, TR is less than 1, so it is nearly equals to 2, right? You see, what is the difference here? So it is nearly equals to 2. So that means the structure, I mean, visualize the force or the, what should I say, structure, visualize or sees the excitation like a suddenly applied load. Okay. So that you have already seen, right, 2 times for the undamped system. So that is what. So through this response spectrum, I mean, everything you can just explain, right? So all those plots that you have shown here, all the calculations, so this is actually represented here. You see when tr by tn, again I am repeating, so when tr by tn equals to 1, 2 or like that 3, so you can see, so it is the static solution, system doesn't oscillate. And you see the responses are going very close to the static solution, that is DLF1. DLF1 means static solution, right? That is extreme as delta st, correct? So that is also clear in this figure, say. You can see as the tr by tn is more, there is 1.5 or 2.5, that is system oscillate close to the static solution, that is the shown through the dot line, I mean dash line. Okay, and when it is tr by tn, it's much less, I mean the less than 0.2 or something around this range, so it is the DLF is 2. So that means the structure feels that, or structure sees that the external excitation like a suddenly applied force. Okay, correct? Okay, so the response spectrum actually defining everything. So you can just whatever I am just told, that is written here. Okay. Okay. So what we have discussed? So discussed the step function load, then ramp function load, and then the step load with the finite rise time. So these 3 things we have discussed. Okay. So based on these things, we will next discuss about some of the pulse excitation, very short duration, just load and then finish. Okay, like as I already mentioned, it can be rectangular pulse, a small duration, it can be triangular pulse of this shape or this shape, or a half sinusoidal pulse of this. Okay. So obviously I am not going to consider all those things. Okay, I will just concentrate on either this or this. We can read the rest of the things in a similar manner from any books. Okay, so maybe I will consider only this only. Okay. So that is the rectangular pulse force. Okay, very short duration load like the blast type of load. So that is the air pressure actually generated by the blast load or any other explosion like that. Okay. So this that is actually idealization, right? So I will show the in the next slide. It is there most probably. What you can see. So this is the actually the pattern of the blast load of the expression due to. So this can be idealized as some type of triangular type of load or a sine pulse load, or sometimes even QT is a rectangular load. Okay. So these are the subject of much lot of work during 1916 and 1970s. Lot of work has been done, and there are the basic idea is to form the shock spectrum. You see, because as we have just shown right through the response spectrum, which is for this pulse excitation or the shock, it's called the shock spectrum. We can find out what is going on, right? And at for different values of TR by TN or like those things. Okay. Right, so that we are going to discuss, and what is written here: response to such pulse excitation does not reach a steady state condition. Yeah, so it is for a very short duration, right? So will not reach to the steady state condition. So effect of the initial state condition must be considered. So that's why, yeah. So what we actually will study here. So let's say this is a triangular, a rectangular pulse load. Okay. So we'll study during the pulse what is the response. After that pulse also we have to consider what is happening due to the initial condition that it imparted at the end of this pulse. Okay. So that we will also consider. So you may find in some books. So this name of the chapter. So in some book it will be response due to arbitrary loading, response due to shock impulse loading. In some book it is written at the transient response. Something like that. Okay, so that we'll discuss in the next class. Okay. So now I'm not going to start that thing. So if you have any doubt regarding the today's class, that you can ask. So as mentioned by CR, who told, I do not remember the name. So our first which one will be on, I think 8th, right? If I remember correctly, 8, 9, 2021. Time which I think 12:30. So whatever minute I'll give, 35 minutes or 45 minutes. Okay. So be prepared for that. Okay. And try to finish that within the time, because since it is to the MS form, so if you delay, then it will not be able to submit it. And the time I am providing is more than enough. Okay. Okay. So tomorrow is your basically the last class before this quiz one, right? Because in the next week, 6 to 8 is the, I think the first assessment is declared. So and during that period, no classes will be there. So tomorrow class, I'm thinking that I'll consider this as a doubt clearing classes if required by you. So please by today evening, will let me know whether you have the requirement of such a class. Okay. If many people say that it is required, we have a lot of doubts, then we can conduct the tomorrow's class as a doubt clearing classes. Okay. If there is a very few people, let's say less than 10 people, then they can contact me directly. Then do not need to waste the next class. I'll just continue with whatever we are discussing. That means the shock loading we will discuss. So you just decide and please let me know by today evening. Okay, so that I can plan accordingly. Okay. You understood what I am telling? Class CR is here or CR is not here? CR.
Yes, sir.
Yeah. So understood that what my proposal is?
Yes, sir, understood, sir. We will ask it and we will inform you by evening, sir.
What?
Yeah, we will ask to our classmates and we will inform you by today evening, sir, about tomorrow's doubt clearing session or not, whether it can be a normal class.
Yeah, right. Yeah. You just tell me by today evening, and this is the timing. So that's finalized by this year, 8, 9, 2021, 12:30.
Yes, sir.
Yeah, obviously. Okay. So it is. I am not forcing you in anything that today, tomorrow class has to be the route clearing classes or nothing. You just decide yourself. I think it is. If you feel that it is not much to there to waste 50 minutes, so then you can continue with the normal classes. Okay. So just. But if many people has doubt, or they want to ask, so then we can consider the tomorrow's class as a doubt clearing session. Okay. Fine. So today I will stop early because I do not want to start the next thing. There is a shock. So I'll give the shock maybe in the tomorrow classes. Okay. And then we'll solve one problem. So I'll just consider one either triangular pulse excitation or the rectangular pulse, any one of them, and other one or two. This in a similar manner you can read from the books. Okay, and we'll solve one problem also regarding that. Okay, and with that we will finish the response into arbitrary body. And actually, in the end of this is the end of that will be the end of actually single degree of freedom system. Although there are many topic is there, but for this elementary structural dynamics courses, this much is good enough. Okay, with the one thing is that remaining, that is the response calculation through numerical approach, right? So that, as I already mentioned, I will discuss maybe after finishing the multi-degree of freedom system, because you see the solution what we are solving is that a mx double dot, if it is undamped system, plus kx equal to some force, right? So this is equally applicable for multi-degree freedom system. So now we are doing for single degree freedom system. For multi-degree freedom system, this is a matrix, right? K and M matrix, X will be vector. So that we will see soon, maybe in the next week, right? When we will start the multi-degree freedom system. Okay. So first we will start with the 2 degree of freedom system. The convenience. Okay. Okay. So please let me know by today evening. Okay. Or you have any doubt in today's class that you can ask. I'll be here for the next 5 minutes. Or otherwise, the class is formally over. You can leave.
Sir.
Yes.
So can you explain that point one more time? That steady state, previous slide, pulse excitation.
This one.
Yes. The last point.
This one. This one.
Yes. So like steady state, it is having it is coming to zero. Then.
No, steady state is not coming to zero. Right. You see,
like it is reaching a particular value at last.
Yeah, correct. That is called the steady state. So in these cases, you see this load is stopping here. It's sudden just for a short period and then finished. So it will not be a steady state. Very short period. So now I think you understood your doubt. You are saying that here it is steady state reaching, right? Correct?
Yes, sir.
Yeah, but it is a continuous. The force is there, right? Correct?
Yes, sir. Got
it. Force is there. Here it is finishing.
It will be a gradual change.
Very short duration. Very just finished, blast, right? Explosion. How much time it takes? Yes. So that's why it's called the transient response. In some books, it is written like that. Okay. So read from books to gain confidence. Okay. These PPTs classes are just to initiate your structural dynamics concept, and basically this is introductory type. Okay. So read more from the books. You'll find it is far more interesting, okay, than what we are discussing for this very short period. Okay. So please let me know by today's evening, okay, whether you record or not. Okay, fine. So we'll meet tomorrow.